This is section 8.4, trigonometric substitution. Basically, you can use trig substitution to find integrals that contain radicals. So specifically, these three radicals here. The objective is to eliminate the radical completely, and you can do that by applying these Pythagorean identities. So these are the same identities that we've had before, but it's helpful to make sure you know them. And of course, there are different variations to each of these if you add or subtract a value. So basically, here's how it works. If we have this here and we let u be a sine of theta, and I plug that in here, then you square each of these to get this. If you notice that these two terms have an a squared in common, you can pull out that GCF of a squared, and then you're left with this, which by a trig identity is this. By properties of integrals, you can then take the square root of these separately, giving you this result here. And again, this is nice because the radical has been eliminated here. So basically, if you have an integral involving something that looks like this, then you want to let a be equal to, you want to let u equal this. In this case here, this is the only one of the three that involve addition. You will let u equal this. And then this one here, you will let u equal this. And these values simply come from applying the Pythagorean theorem or SOHCAHTOA, that sort of thing. So take a look at this chart, see if you can understand what's going on, and let's look at our first example. In this example, it says find the indefinite integral using the substitution x is equal to 4 sine of theta. So I'm going to show you the steps that it takes in order to solve or to evaluate this integral. Okay, so the first thing you'll want to do is you will want to find the derivative of this. So you want to find dx d theta, and when you do, you have dx is equal to 4 cosine of theta d theta. Okay, now this is helpful because at some point we are going to substitute this in here for dx. Okay, now what we want to do in step 2 is we want to try to see which of those substitutions we want to use. And our goal is to eliminate this radical. So it tells us what substitution to make because our goal is to only have thetas here. We want thetas in this rather than x. So we know that x is 4 sine of theta. So I'm going to go ahead and make that substitution. And so again, I'm only working with this radical right now. So this becomes 16 minus 4 sine of theta squared. All right. This simplifying further, if I square everything here, I get minus 16 sine squared of theta. I have a 16 in common, so I can take that out. So I have 1 minus sine squared of theta. I can write this as the square root of 16 times the square root of cosine squared by applying the Pythagorean identity. And then this becomes 4 cosine of theta. So this simplifies to 4 cosine of theta. So we're getting closer to only having thetas in here. So the only thing I need to do is replace this with what I was given. So let's give that a shot. This becomes, so this is step 3. We have the integral of 4 over x squared, which is 4 sine of theta squared by substitution, times 4 cosine of theta, which we found down here, times dx, but we have found dx to be this, 4 cosine of theta d theta. All right, so now we want to clean this up a little bit, and I can do so by putting this over 1, multiply across the top, across the bottom, and when I do that, hopefully you'll notice that the cosine of thetas cancel, and then all the 4's end up canceling too. So I end up, I'm sorry, not all the 4's because this one's squared. I apologize. So I end up with 1/4 times the integral of 1 over sine squared theta d theta. Okay, well now 1 over sine squared can be written as cosecant squared. Okay, so continuing on, if I integrate this, I have 1/4, I'm sorry, it's actually negative 1/4 cotangent of theta plus c. Okay, so here's the kicker. Before we wanted theta, all right? So now we have everything in terms of theta, but our answer is going to be in terms of x. So I don't want theta anymore. So this is when I'm going to apply our trig substitution type thing. Okay, so this is going to be step 4. I was given that x equals 4 sine of theta, which means sine of theta is equal to x over 4. Now, if I apply SOHCAHTOA to this, then if sine of theta is x over 4, and this is theta, then I know that this is x, this is 4, which means this is the square root of 16 minus x squared. And you can find that by applying the Pythagorean theorem. Okay, well, this is helpful because I want to use this triangle here in order to figure out what cotangent of theta is. Because if I know all of these sides, I can find all 6 of my trig functions. So that brings me to step 5. Step 5 is equal to negative 1/4 times the integral of, so it's the reciprocal of tangent. So TOA is this. Excuse me, this is squared plus c. If you want to kind of clean this up and write it as one fraction, you'll have negative radical 16 minus x squared all over 4x, and then the plus c since it is an indefinite integral. So let's look at yet another example. All right, so remember, step 1 is to find dx. So if I find the derivative of this, I get 5 secant theta tangent theta. d theta. All right, step 2 is to try to get rid of this radical. Okay, so we're going to use some substitutions and see what happens. So this x, so step 2, this x goes in here. So just focusing on the radical, I get the following. This needs to be squared minus 25. Continuing on, I have the square root of 25 secant, secant of theta squared minus 25. I can take that GCF out. So this is 25 times secant squared. This can be written as tangent squared. So taking the square root of each of these, if this is tangent squared, then this simplifies to 5 tangent of theta after taking the square root. All right. So instead of this radical, we have this. Instead of dx, we have this. And instead of x, we have this. So we are going to rewrite this in step 3. So we end up with 5 tangent of theta over 5 secant of theta times dx, which is 5 secant theta tangent theta d theta. All right, with some simplification, these 5's cancel. If I put this over 1, I'll find that the secant cancels out also. So I'm left with tangent squared times 5, or the integral 5 times tangent squared of theta. All right, finding the antiderivative of tangent squared is a little tricky. So we will rewrite this using secant, or the Pythagorean identity. So this is secant squared minus 1. Continuing on, I get 5 times tangent, because the antiderivative of secant squared is tangent, minus theta, because that's my variable, plus c. Okay, now from here, remember, I don't want thetas anymore. So since I don't want theta, in step 4, I'm going to use the given and draw my little triangle. So if I'm given x equals 5 secant of theta, then I know that secant of theta is x over 5. If I know secant of theta, then I can certainly find cosine of theta because they're reciprocals. That's 5 over x. With this, I can construct my triangle. Here's theta. So applying SOHCAHTOA. So cosine is the adjacent over the hypotenuse, and then you can use the Pythagorean theorem to find this missing side, which is the square root of x squared minus 25. Okay. All right. So this is all very helpful information. And we're going to use this to find tangent. Okay. Now, the thing is, I also need to find theta. So finding tangent shouldn't be hard by using this, but I have to find theta. So in order to find theta, I'm going to use the given information that I have, and I'm going to get theta by itself. So I suppose you could call this step 5. Let's come up here a little bit. So here's step 5. Again, this is to find theta. Okay. Now in the previous example, I didn't have a theta to find. I only had the trig function. So this is an additional step. Okay. So we know that x is 5 secant of theta. So I can divide by 5. So this is secant of theta. And then I can take arcsecant of both sides. And when I do, I get arcsecant of x over 5 is equal to theta. So now I'm going to substitute this in here, find tangent, plug it in there. So this becomes 5 times tangent of theta, which is x squared minus 25 over 5, minus theta, which is secant inverse of x over 5, plus c. And there you have it. If you want to distribute this 5, you can. If you do distribute this 5, you end up with something a little more simplified. It's up to you. Final answer. Okay, in this example, things are a little bit different because now I don't have a radical in my integrand. So what I need to do is the same type of thing, but instead I'm just going to make a bunch of substitutions. So step 1, I need to find dx just like before. So dx is equal to 2 secant squared of theta d theta. Now plugging in everything just right into here, I end up with the integral of 2 times 2 tangent of theta squared all over 4 plus 2 tangent of theta squared, all of that is squared, times dx, which is this. Okay, so there is some simplifying involved. I can multiply across the top, across the bottom. When I do, I get, oh, this is squared, so this is 4 times 2 times 2, giving me 16 tangent of theta squared secant of theta squared all over. Then this is 4 tangent of theta squared. So I have 4 plus 4 tangent of theta squared squared. All right, continuing on. Simplifying the bottom. This gives me 4 times 1 plus tangent squared, which is secant squared. So I have 4 secant squared squared. 4 secant squared squared gives me 16 secant to the power of 4. So some things cancel. These 16s cancel, 2 of these cancel, and I'm left with the integral tangent squared of theta over secant squared theta. This can simplify. Recall tangent squared. Tangent is sine over cosine, and this is 1 over cosine. So I get the integral of sine squared. In order to integrate sine squared, I need to apply the power reducing formula. Recall from a previous lesson the power reducing formula for sine squared is the following. So when I integrate this, this is 1/2 minus cosine of 2 theta over 2. I get 1/2 theta minus 1/4 sine of 2 theta plus c. Now I'm gonna throw back here. sine of 2 theta, I don't know if you remember this trig identity or not, but sine of 2 theta is equal to 2 sine of theta cosine of theta. So this is 1/4 times 2 sine of theta cosine of theta plus c. So I have negative 1/2 minus 1/2 sine of theta cos of theta plus c. So we've come to the part of the problem where we have everything in terms of theta, but we don't want theta. So if we don't want theta, what we do is we use the given information, make a triangle. So we identify that x over 2 is equal to tangent of theta. So applying SOHCAHTOA on my triangle, I know this is 2, this is x. Pythagorean theorem says this is 4 plus 4 plus x squared. Oh my goodness, I can do this. Okay, so this here is all I need these two things to find theta, because I take arctangent of both sides. And this can help me find sine of theta and cosine of theta. And I'll let you go ahead and do that and just tell you what the answer should be. When all is said and done, you should end up with 1/2 arctangent of x over 2 minus x over x squared plus 4 plus c. That's the final answer. Trig substitution comes in some different forms also. So these special integration formulas are helpful, so you can pause and take a look at this. But what's different here is we're just going to apply these formulas. So it's helpful to be able to identify what you're given. If you don't have a fraction like we had in the previous examples, then chances are you'll want to use one of these. And I'll show you how to apply it. So here we have something a little more straightforward. I have 9 plus 4x squared under the radical. If I look at this, this falls under the third special integration formula. So I need to identify u and du and a according to that formula. So from here, I'm going to let u equal 2x. All right, and if u is 2x, then du is equal to 2 dx. And I will let a equal 3. So applying the formula, here I need to put a 2 in and undo it on the outside. So applying that formula, I'm going to have this 1/2 here. And then I get to use the formula, which says I have another 1/2 times u. U is 2x times the square root of, it's just the given, plus a squared, which is 9, because 3 squared is 9, times the natural log of the absolute value of u, which is 2x, plus the square root of 9 plus 4x squared, all in the absolute value, plus c. I can simplify this a bit, giving me x over 2 times the square root of 9 plus 4x squared plus this 1/2, this 1/2 in the parentheses is applied to all of this. Sorry about that. So this is 1/4 times 2 is this, and then 1/4 times 9 is 9/4 times the natural log of all of this jazz. Plus C. There you have it.